Hey guys, welcome to the new video with the topic on physics, especially electricity and magnetism. Today I am bringing you a new topic on moving coil galvanometer. A moving coil galvanometer is a sensitive instrument which is used to detect and measure feeble current in a circuit, and even you can find the direction of direct current. Moving coil galvanometer works on the principle that a current carrying coil experiences torque in a magnetic field, because of which it tends to rotate. And it is that angle of deflection of the coil is directly proportional to the magnitude of the current passed through it. Now let us see the construction of the device. Here we are going to discuss the construction of suspended coil type moving coil galvanometer, and I will share pivoted coil type galvanometer as well, but won't discuss in detail about the construction of pivoted type galvanometer. I will share main ideas only. Uh, Moving coil galvanometer, that is suspended coil type galvanometer, consists of a rectangular coil PQRS. You can see shown by somewhat reddish color, that PQRS coil, that is wound on a cylindrical frame that consists of soft iron core. The coil can rotate about vertical axis and is placed in between two concave pole pieces of a permanent magnet. One end of the coil is connected to terminal T1 through hair spring H, and the other end of the coil is connected to terminal T2 through a phosphor bronze strip and torsion head. The current to be measured is passed through the terminals T1 and T2. As the current is passed, the coil will deflect. This deflection is observed with the help of lamp, concave mirror, and scale arrangement. Yes, this is of course older version. You can find the suspended coil type moving coil galvanometer in Google. Actually nowadays this is not in use, and it may be kept as showpiece only. Um, in case of suspended coil type galvanometer, the phosphor bronze strip has to support the weight of the coil. So that phosphor bronze strip is preferable rather than other materials because it has good tensile strength, it is rust free, and its torsional constant is very small. That makes the galvanometer sensitive. How it works? Let us discuss the theory. When A current I to be measured is passed through the terminals T1 and T2. The coil will experience the deflecting torque. That deflecting torque is given by tau d is equal to BINA cos theta. And as the magnetic field is radial, each time there will be magnetic field lines which are always parallel to the plane of the coil, providing the maximum torque. So we can use theta is equal to 0. Other field lines will be deflected without penetrating or without passing through the coil. So radial field or that concave pole pieces provide radial field, increasing the sensitivity of the moving coil galvanometer. As the coil rotates, the phosphor bronze strip is twisted and a restoring torque is developed in the phosphor bronze strip. If the coil remains deflected by angle phi, then restoring torque on the phosphor bronze strip is given by tau r is equal to C phi. Let me share. You can see where C is torsional constant, that is restoring torque per unit angle of twist. When the coil remains deflected by angle phi, that is when the coil is in equilibrium, we must have deflecting torque is equal to restoring torque. So we write tau d is equal to tau r, and by substituting the values from equation 2 and equation 3, we get BIN is equal to C phi. Next, from this we can write I is equal to C upon BAN into phi. The terms inside the bracket are constant for a given galvanometer. So we write I is equal to G phi, where G is equal to C upon BAN. This is a galvanometer constant. So from this expression, we can see that the current and angle of deflection are related linearly, just like y is equal to mx. I and phi are related linearly. This means we can observe magnitude of current, or we can measure magnitude of current by observing the deflection of the coil using linear scale. Okay, only because I and phi are linearly related. If they were not related linearly like this, we could not use the linear scale in the moving coil meters. Yeah, here I have shown the pivoted coil galvanometer. It consists of two coils at the two ends. of the rectangular coil. Both are made of phosphor bronze, and that will develop the restoring torque in this case. In case of suspended coil type, phosphor bronze strip has to support the weight of the coil as a whole, but in this case, they will bring the coil back to initial position only. That means they are kept to develop restoring torque. Let us now discuss the current sensitivity of the moving coil galvanometer. Current sensitivity is defined as the ratio of angle of deflection of the coil per unit current passed through it. It is denoted by SI. So we write current sensitivity SI is equal to angle of deflection upon current. That is SI is equal to phi upon I. For galvanometer, we have BINA is equal to C phi. Just now we discussed that. From this we have phi upon I is equal to BAN upon C. That means SI is equal to BAN upon C. This expression shows that the current sensitivity of moving coil galvanometer can be increased by increasing the strength of the magnetic field and choosing a coil of larger area and having large number of turns. The current sensitivity can also be increased by choosing the material with small value of torsional constant C. If we increase A and N, that will increase the length of the wire. Hence, the resistance R of the coil is increased, which in turn causes the decrease in sensitivity of the moving coil galvanometer. So, increasing N and A is not preferable to increase the sensitivity. Only it is preferable to increase the strength of the magnetic field and choosing the material with smaller torsional constant C. Remember this is very important point. Now, voltage sensitivity of moving coil galvanometer is defined as the deflection produced in the coil per unit potential difference applied through or applied across its terminals or across its ends. It is denoted by SV. So SV is equal to phi upon V. You know the coil is ohmic, so we can substitute V is equal to IR. And phi upon I is just SI, the current sensitivity. So SV and SI are related. SV is equal to SI upon R. This is also important relation. And the voltage sensitivity depends on ohmic resistance. I have here some short questions related to moving coil galvanometer. Let me see here. You can just pause them and copy for your examination point of view. First question, what is the function of soft iron core in moving coil galvanometer? Yes, the soft iron core strengthens the magnetic field That in turn increases the sensitivity of the moving coil galvanometer. Soft iron core. Iron is, ferromagnetic material that consists of ferromagnetic domains. So the ferromagnetic domains will align in the direction of the magnetic field, thereby strengthening the magnetic field. Next, 2-number question. Why is phosphor bronze strip is used in moving coil galvanometer? Yeah, I already explained. Phosphor bronze strip in suspended coil type galvanometer has to support the weight. So it needs greater tensile strength. Of course, it has a high tensile strength. It is rust resisting alloy, and its restoring torque per unit angle of twist or torsional constant is very small. That makes the galvanometer sensitive. Because of all these reasons, phosphor bronze strip is preferable. Next question. What is the use of air spring made of quartz in suspended type moving coil galvanometer? Okay. Uh, let us suppose we use any other material than the air spring made of quartz. Then imagine that when the coil rotates, the other materials will be twisted and may be broken. In the form of air spring, this will reduce the elastic after effect. And quartz has negligible elastic after effect. As the current is to be passed through, it must be good conductor of electricity. Quartz is good conductor of electricity. Young modulus of quartz is greater, and there is no elastic limit. So air spring that is made up of quartz is used. In the lower part, that means as we have shown in the lower part of the coil in our diagram. Thank you very much. Enjoy the learning, and you may comment the topic you may need for discussion in next video. Thank you.